Hello from the Narrative Intelligence Lab. I'm Stephen Ware.
And I'm Corey Seiler.
And today we're excited to tell you about the Sabre Narrative Planner, the successor to our previous narrative planner, Glaive, which has been under development on and off for about the last 7 years. Narrative planning is an interesting and challenging problem, where a single centralized decision maker generates a sequence of actions to tell a story, but all the characters in the story need to act believably. While the author might be omniscient and omnipotent in the virtual world that they create, individual characters need to act according to their own possibly wrong beliefs and their own goals, which might cause them to cooperate or conflict with other characters. A classical planner generates every possible sequence of actions, but not every sequence makes a good story. There's been significant previous work on intentionality, where agents appear to act in service of their goals. For Sabre, we've changed from propositional goals to utility functions, which allows our agents to express complex preferences over different types of goals. There's also been significant prior work on allowing agents to have their own possibly wrong beliefs. In our previous work, we generated stories from every region of this Venn diagram and confirmed that stories in that purple region represent the most believable agent behavior. So Sabre is a planning algorithm that generates a sequence of actions to improve an author-defined utility function. But every time an agent takes an action in the story, that agent has to believe that the action could contribute to improving their own utility. In this video, we'll be using an example problem from a prototype interactive narrative game that's controlled by a narrative planner. In this game, the player or protagonist, Tom, is sent to the market to buy a potion from the merchant. The logical language that Sabre uses is similar to Helmert's multi-valued planning task. We describe the world as a collection of fluents. A fluent is really just a variable, like this one that represents Tom's current location, and that variable can be assigned one of any number of possible values. For example, we can say that Tom is at the cottage. Sabre supports several kinds of fluents, including Boolean values and even numeric values. Sabre also supports the modal believes predicate, that allows us to specify what characters believe the value of every fluent to be. This believes predicate can be arbitrarily nested, so for example, we can talk about what the merchant believes that Tom believes. While Sabre supports an arbitrarily deep theory of mind, it does not support uncertainty. In other words, characters can't believe X or Y, they must always commit to their beliefs, even if those commitments are wrong. We chose this particular combination of features because it allows us to tell a wide variety of stories, but it also keeps the search space of problems small enough that we can solve at least some non-trivial problems online in real time during gameplay. The planner also supports a handful of other useful syntactic features that we won't go into here. The bread and butter of a planning problem are the actions the user defines. These are events which can change the state. For example, here Tom is buying the potion from the merchant at the market. We'll call this action A. Actions have a precondition, so for example we'll say that Tom has to be at the market, the merchant has to be in the merchant has the potion, and Tom has at least one coin. Actions have an effect which describes how they change the world, so here Tom has the potion, the merchant has one more coin, and Tom has one fewer coin. They also define consenting characters. These are the characters that have to believe this action could help to improve their utility, in this case Tom and the merchant. We also have an observation function defined for some character C, which says who's going to observe this action. Here we're saying that everyone in the market is going to notice this action happen. If you notice the action happen, you update your beliefs as if it had occurred. If you don't notice the action happen, in other words, if you weren't at the market, then your beliefs don't change unless the effects of the action explicitly modifies them. Actions are things which can happen, but Sabre also lets you define triggers, which are things that must happen when their preconditions are satisfied. For example, we might say that when Tom is at the market and the merchant is at the market, but Tom believes the merchant is somewhere else, now Tom believes the merchant is in the market. This is a common use case for triggers. For example, let's say Tom had a wrong belief about where the merchant was, but then walked to the market. We would want him to notice that the merchant is there. Any number of triggers can run after an action occurs. Before Sabre starts looking for a solution, it does some pre-processing on the problem. Actions and triggers have explicitly authored effects. For example, when Tom buys the potion from the merchant, Tom has the potion. But they often imply an infinite number of additional results. So for example, Tom knows he has the potion, the merchant knows that Tom has the potion, Tom knows the merchant knows that he has the potion, and so on. Events might have an infinite number of results, but thankfully they have a finite number of preconditions. Sabre looks at the preconditions across every action and trigger in a problem to calculate every precondition that might ever get checked. Then, when it's calculating the results of events, it only calculates those results which might be relevant to that set of all possible preconditions. Another useful feature of Sabre's preprocessing is the ability to detect fluents whose values will never change, and actions and triggers that will never occur. Let's say you wanted all the paths in your virtual world to be two-directional. Here's a specific ground instance of a trigger that says if there's a path from the cottage to the market, there should also be a path from the market to the cottage. This trigger is going to run once in the initial state, and assuming there aren't any actions that change paths later on in the story, this trigger is never going to run again. Sabre can recognize this, apply these changes in the initial state, and then remove the trigger from the problem. Because the path from the market to the cottage is always going to exist, Sabre can also find preconditions that contain this proposition and simplify them to make search easier. Here's the Sabre planning algorithm as given in the paper. This video gives an example to help you walk through that pseudocode. We begin in the initial state, where Tom has some money and is at the cottage, and the merchant is at the market with the potion. According to the author's utility function, we're trying to tell any story that ends with Tom being at home with the potion. Let's say the first thing that happens is that Tom walks to the market. In the paper, we use this notation alpha to indicate that if you're in state S0 and take this action, you would now be in state S1. Tom is the consenting character for this action, so to include it in the story we need some explanation for why Tom would go to the market. To do that, we're going to have to look at what he believes. This is the notation we use in the paper to talk about character beliefs. If the state is actually S0, Tom believes the state is S2. Sabre does not support true uncertainty, so that beta function is always 1-to-1. S2 represents what Tom thinks the state currently is. We're trying to find an explanation for why Tom would go to the market. To accomplish this, we're basically running a smaller planning problem that starts at state S3 and is looking for any state where Tom's utility is improved. Suppose Tom buys the potion. This action has two consenting characters, the merchant and Tom. Tom's the one forming this plan, so we don't need an explanation for him, but he has to anticipate that the merchant would be willing to participate. We're going to need to reason about what Tom believes the merchant believes. The merchant just wants money. Her utility is equal to her number of coins, so thankfully in state S6 her utility has improved, and we've got a clear explanation for why the merchant would be willing to participate in that action. So now Tom is free to complete his plan. If he walks home, his utility will increase to 1 because now he's home with the potion. So that explains why he'd be willing to walk home and why he'd be willing to buy the potion. All of that contributes to the explanation for why Tom is willing to go to the market. He's willing to do it because he can imagine a way that that action might increase his utility. Now the author can choose the second action in the story. Let's say the author chooses for Tom to buy the potion. Remember, two consenting characters, the merchant and Tom. Their explanations are just shorter versions of the ones that we found before. The merchant's willing to do this because she gets more money, and Tom is willing to do it because he can imagine a plan where this leads to him getting home with the potion. Now the author's free to choose a third action. Let's say Tom walks home. This is going to get explained in the same way. Tom does it because he thinks it could increase his utility. Finally, we've reached state S14, where the author's utility has improved because the story goal has been achieved, and every action that we took along the way to state S14 can be explained for the consenting characters who took those actions. This is what Sabre considers a solution to the problem.
In the planning world, it's common to run a new system on a set of benchmark problems alongside previous systems in order to compare their time and space efficiency. However, the problems that Sabre solves are not quite the same as the problems solved by any other system, so it's hard to make a fair empirical comparison. I'll show you what I mean. Recall that Sabre is a centralized planner that requires characters to act consistently with their intentions and beliefs, and that the belief model does not include uncertainty about the state of the world. The Sabre model builds on existing planners like Glaive that handle intentionality but not belief. Prior belief-based narrative planners include Headspace, where characters' actions can fail if they wrongly believe the preconditions are met, and Impractical, which combines belief with character goals. But neither of these systems allow for deeply nested theory of mind. Frameworks like Talk of the Town and Thespian feature characters who reason with deep theory of mind, but these are multi-agent systems, where character actions are truly autonomous rather than centrally planned. Ostari is the only system we've encountered that's expressive enough to do everything Sabre does, but it's built to handle a sophisticated belief model where characters can reason about multiple possible worlds, and in our preliminary tests, it didn't scale well to problems designed with Sabre's simpler belief model in mind. Because Sabre has a unique set of features and there's no straightforward way to make a direct empirical comparison to other systems, we instead offer some raw benchmark data to give an idea of Sabre's current capabilities. To get some of our benchmark planning problems, we took problems from Glaive and added belief. Some other existing benchmarks were already designed for combined belief and intentionality models. We wrote one domain to imitate a subset of the story space from the classic story generator Tailspin. And one comes from the narrative game featuring our hero Tom from earlier. Here are the amounts of time it took for Sabre to solve these problems, as well as the number of search nodes generated. Sabre can generate a lot of search nodes very quickly, but even so, some of the harder problems took minutes or hours to solve with the current heuristic. More research into heuristics could someday make Sabre fast enough for playable applications, as we saw with its predecessor Glaive. See the paper for additional details and experiments.
Sabre has several obvious limitations. The biggest is probably that we don't model true uncertainty, so certain kinds of stories, especially mystery stories, can't really be told with this system. Also, the default heuristic dramatically underestimates for a lot of our example problems. Our current implementation tries to explain every action before adding more actions to the story, but you could easily imagine a version where we first find a sequence of actions to achieve the goal and then work backwards to try to find explanations for them, or some hybrid approach. In fact, this is the subject of a forthcoming article that we're already writing. We're also developing some better heuristics and hoping to integrate Alex Shervani's recent work on emotions and personality for plan-based agents to expand the richness and the kinds of stories that Sabre can generate. Thanks for listening. We're hoping to release the source code for Sabre sometime next year, and we hope you'll find the project useful.